Welcome to a new advanced geometry lecture. We will go ahead and provide a new proof, a second proof for theorem 1.81 in section 1.8, page 20 from the book Geometry Revisited by Coxeter and Greitzer. Here's a view of the theorem again. In this new drawing I made some additional lines here. First of all, we added the circumcircle, and also we extended the altitudes to meet with the circumcircle. And also we did draw the rays starting from the orthocenter to the midpoints, and we extended them to meet with the circumcircle as well. The key idea of this second proof is the fact that at the end of the first proof, in order to establish that the radius of the 9-point circle being half of the circumradius, we've made the observation that there is a homotety centered at the orthocenter with a factor of 2 basically, which would take our triangle LMN and it will map it onto triangle ABC. Obviously this works because, well, we established that HM is equal to MB, well, the definition of the point LM and N, and we also know that HN is equal to NC and AL is equal to LH. And because LM and N are defined as such, it's possible to construct this homotety. And also we established that the circumcircle of LMN is the 9-point circle, because 3 points define a circle, and therefore the homotety would also take the 9-point circle onto the circumcircle. All we need to do now is to establish that the feet of the altitude and the midpoints of the sides are basically the midpoints of these rays from the orthocenter to the circumcenter. Let's go ahead and establish those results. The best way would be to consider reflections. So let's focus on our orthocenter again. So let's consider a reflection of our orthocenter, and let's call that reflection H1. Reflect H across BC and call it let's call it H sub 1. So obviously it would be on the line somewhere on HD, or HD1, or beyond D1 actually. We don't know where exactly, but so we're reflecting H onto the other side of the point D, so somewhere over there. Okay, so where is that located? So let's do some angle tracing here. So consider this angle BH1C. Obviously by reflection, it would be equal to angle BHC, but it turns out that with simple angle tracing, angle BHC is nothing but 180 minus angle A. To view that, just observe that considering triangle BEC, this angle over here, angle EBC, is simply 90 minus C. And also now focusing on triangle BFC, you just realize that angle BCF is 90 minus B. Now going back to triangle HBC, this third angle here would be simply, they should add up to 180, so therefore it would be simply B plus C. But B plus C in triangle ABC is nothing but 180 minus A. So this establishes our result. However, now we observe that H1, angle H1 or BH1C, and A are supplementary angles. Therefore, we can say that points B, H1, C, and A are concyclic. But then this immediately implies that H1 is the same as D1. So D1 is basically the reflection of H across BC, and as such it implies also that HD is equal to DD1. And similarly you can also establish that HE is equal to EE1 and HF is equal to FF1. Now all that is remaining is to show that really point I is the midpoint of hi sub 1. To do that, I will use a similar trick. This time we will reflect h across the point I, reflect h across I, and call it, I don't know, let's call it h sub 2. So first we observe that, well, obviously by the reflection property, hi is equal to ih2, and, well, we also know that bi is equal to ic. As a result, this implies that bhch2 is a parallelogram, obviously. It's possible to conclude that by angle tracing, bh2c is equal to, recall that h2 is somewhere on this line here between I and I1, or beyond I1 actually. So bh2c is nothing but bhc. But again, bhc, we know bhc is equal to 180 minus a. So therefore, it must be the case that therefore b, a, c, and h2 are concyclic, So it must be the case that h2 is on the circumcircle, but we know that point is I1, so I1 is nothing but h2, it turns out. So that establishes the fact that therefore, and so we can also say that hi is equal to I1. And in a similar way, you can easily prove that hj is equal to jj1, and hk is equal to kk1. Now finally, to conclude our proof, all we need to do is to consider again that homothety centered at point H, but this time the one that takes the circumcircle and maps it onto the 9-point circle. Well, obviously it would immediately imply that E1 would be mapped onto E, F1 would be mapped onto F, D1 would be mapped onto D, because we know these distances are half of the distance. D is the midpoint between H and D1, and so on. So, and in a similar way, I1 would be mapped onto I, J1 would be mapped onto J, and K1 would be mapped onto K as a result of this homothety. So this transformation, this homothety with a factor of 1/2 would shrink our circumcircle into the 9-point circle. But wait, there's an additional benefit of that. It actually also gives us a clear view of the location of the center of the 9-point circle. Obviously, when you think about it, the center of the circumcircle, let's call it O here, so it's immediate that the homothety will take this center of that circumcircle onto the midpoint of the line segment HO, right? So that would be the center of the 9-point circle. Let's call it P, I guess, point P here. And so this is a beautiful result, because it also immediately implies that because HO defines the Euler line, so the center of the 9-point circle is basically the midpoint of the segment HO between the orthocenter and the circumcenter. So that would basically conclude the second proof of this beautiful 9-point circle, and of this theorem basically. So that's the end of our short lecture, and see you in the next video.